or maybe an evangelist somewhere, but you turn the dial and eventually you hit a really nice mariachi band. So our speaker today is doing a similar thing, but when you turn the dial, what you're supposed to discover is the dark matter of the universe, a very exciting proposition. So Chelsea Bartram got her undergraduate degree, I forget where.
Boston University.
From Boston University, did some beautiful precision nuclear physics experiments for her PhD at North Carolina. Then she got the opportunity to work with some people who are actually friends of mine at the University of Washington to search for an exotic kind of dark matter. And now she's here as a Panofsky Fellow at SLAC working on similar experiments, which she will describe to you. So I hope you all welcome Chelsea, and we'll hear about how to tune into the dark matter airwaves.
Thanks, Michael, for that wonderful introduction, and thanks to everyone who showed up today. It's great to see all of you. But before we tune into the dark matter airwaves, I want to give you a little bit of background on myself. Because in fact, I've been interested in radios since I was a little kid. And this interest has continued through to this day. In fact, when I was in college, I was doing my degree at Boston University, like Michael just mentioned, and I took the train all the way from Boston to Gloucester. You can tell I'm a New Englander, and went ahead and took an amateur radio license. And so this was a test, basically, in order to be allowed to use radios to talk to people in different countries and operate what we say on air. And so fun fact is that they actually took a picture of me taking the test and posted on their webpage here. The young lady is a product of Boston University, where she is taking graduate classes in physics. Her name is Chelsea Bartram, KDAHNZ, so that's my call sign. And you'll immediately be happy to learn she passed and was transported back to the commuter rail station for her return trip back to Boston. And so what they didn't mention is actually I would leave Boston shortly after to attend graduate school in Chapel Hill, as was just mentioned. But I never lost that passion for radio. And so to me, although I was pursuing this PhD in nuclear physics, all the while I was still thinking about radios as a hobby. And so designing radios became a game to me. With a few supplies and a lot of creativity, you could talk to someone on the other side of the globe. You could even reflect signals off the moon. And you could observe the effects of the sun on the Earth's atmosphere. You can then imagine my astonishment when I realized you could also use them to look for dark matter. But how? What is the dark matter? Dark matter is an invisible material that makes up 85% of the mass of the universe. And so everything that we know, everything that we can see and touch, consists of visible matter, which is only 15%. And the pun I always like to make is gray matter is 100% necessary to go ahead and detect it. And so what is the evidence for dark matter these days? One of the biggest pieces of evidence comes from rotation curves of galaxies. And so in around the time of the 1950s, some scientists, including Bear Rubin, shown here, measured how fast the matter rotates in galaxies compared to the radius of the galaxy. And so you can see this plot. And in fact, what we observed was not what we expected. And so you can see there's actually this giant gap here, this discrepancy between what we observed and what we expected. And what we believe today is that this gap can be explained by the presence of dark matter. And so the galaxy rotates in a way that was inconsistent with our understanding of mass and gravitational force. And by adding more mass, we can accommodate for this discrepancy. But what is the dark matter? Now, you may have heard of something called the WIMP, which stands for weakly interacting massive particles. These are very light particles that, if they exist, they can also account for all of the dark matter. But WIMPs behave like particles. In other words, they recoil off of atomic nuclei, like billiard balls. But matter can behave like particles, or it can behave like waves. And I'm here today to tell you about wave-like dark matter. And to understand that, we first have to understand a fundamental premise from quantum mechanics, which is the concept of wave-particle duality. And so many decades ago, scientists performed what we call the double slit experiment, whereby they took an electron source and shot electrons through two slits shown here. The electrons then impinge on a background screen, one by one. And so this, as you see, demonstrates particulate behavior because they go through either one slit or the other, and then the image is shown on the screen. But if enough of these accumulate, you actually see an interference pattern. So this is not consistent with the idea of particulate behavior. And in fact, when sufficiently small quantum objects like electrons pass through a pair of closely spaced slits, they can behave like particles. But then when enough of them goes through, they start to behave like waves. And so this interference pattern is a result of wave-like behavior, as shown here. And so the type of dark matter that I'm interested in is what's known as the axion. And we call it wave-like dark matter. And this is because this dark matter behaves more like a wave than it behaves like a particle. Because of this sort of quantum nature of that I just described, protons and other particles can have an associated wavelength. The wavelength of the proton is on the order of 10 to the minus 12 meters. That is a decimal point followed by 12 zeros, so incredibly small. WIMP dark matter, on the other hand, is something like 10 to the minus 13 meters, so also incredibly small. The axions, on the other hand, their wavelength is something on a scale of 100 meters, maybe 10,000 meters, maybe 100,000 meters. And so this is an extraordinary wavelength for any particle. And we have never encountered such a particle before. In fact, it can no longer be described as particulate in its behavior. And so what do? We can no longer use what we call recoil experiments that we use to search for WIMPs. We have to do something completely different. And so what detection mechanism do we use? Well, axions are thought to turn into photons or light particles in magnetic fields. And this interaction is associated with sort of two key parameters, which I've shown here. We call them GA gamma gamma, which stands for the likelihood or the strength of the interaction. And we use these units, which I'll explain, of 1 over GeV. And then we have the mass of the axion, which is in units of EV. So what is that? Oh, we're back. So EV stands for electron volt, which represents a unit of energy that is equal to the work done on an electron in accelerating it through a potential difference of 1 volt. We all know from Einstein that energy is related to mass by E equals mc squared. And so we often use mass and energy units interchangeably in this field. So you'll often see physicists say things like the mass of the proton is 938 mega electron volts. So that's an electron volt times 10 to the 6. In addition to this, you'll note that energy is also related to frequency. And so high frequency corresponds to small wavelengths, which corresponds to high energy, as you can see in the green vibration at the top. Lower frequencies correspond to large wavelengths and correspond to low energy, as you can see in the blue oscillation at the bottom. And so when we talk about axions, we're talking about low frequencies, low mass, and low energies. Axions have giant wavelengths compared to anything else we know. And their photons, or light particles, would have correspondingly large wavelengths. Large wavelength photons are equivalent to low frequency photons or low energy photons. But how low do you go? Well, we don't actually know what the mass of the axion is, and it could in fact span a very wide range. So here you can see that range depicted in terms of the mass of the axion and the frequency of the photon it would convert to in a magnetic field. At the high end, you see masses of about 10 to the minus 2 eV, and at the low end, you see 10 to the minus 22 eV. So this is quite a large range that we have to cover. And in fact, if we plot it, we can put this mass on the x-axis. So you'll see these plots presented typically amongst axion physicists. Here you see at the bottom end, we have 10 to the minus 12, and we're going up to 10 to the minus 7 or so. So this is just a subset of that range. And then we typically plot it against the interaction strengths, GA gamma gamma. And so here you can see, again, a large range from 10 to the minus 19 all the way up to 10 to the minus 6. And the good news is people have been making progress. And so in this plot, what you see are the colors red, green, and blue, showing different experiments that have probed parts of this parameter space. In other words, they've gone looking for axions and turned up empty so far. The yellow band shown here represents a distinct type of axion, which we call the QCD axion, where QCD stands for quantum chromodynamics. So quantum chromodynamics is the theory of the binding of the atomic nucleus. We often refer also to strong interactions to describe the interactions that cause those nuclei, the atoms to bind together, or the nuclei to bind together. The QCD axion is unique because it solves a long-standing nuclear physics problem. Strong interactions unexpectedly preserve something called T symmetry or time symmetry. This would be apparent to us if a neutron electric dipole moment existed. But so far, no neutron electric dipole moment has been observed. So people have tried to make this measurement and they've turned up empty. And so why is that? This is unexpected. Well, a few folks came up with a solution which they called the Peccei-Quinn mechanism. And I have to mention this because actually one of the inventors of the Peccei-Quinn mechanism has graced us with our presence. So this is Helen Quinn. So thank you, Helen Quinn, for coming. I wasn't nervous at all until Helen walked into the room. And so the Peccei-Quinn mechanism gives us a way to solve the strong CP problem, and it also predicts the existence of this QCD axion. And so these are all the folks that sort of had this realization. And within the broader category of QCD axion, there are actually two classes of models. We call them the KSVZ model and the DFSZ model. And I want to focus in on this one because it is the most difficult to detect, but it is also the most compelling because it can be included in grand unified theories. And so all those of us in the axion community are always pushing to reach what we call DFSZ sensitivity. And I'll use the rest of my time tonight to explain how we do that. So how do we detect it? So the way we go about detecting these very low frequency electromagnetic waves is essentially radios, really, really sensitive, tunable radios in a strong magnetic field. And in fact, the magnetic fields that we use are pretty close to the field strength of MRI magnets. So many of you have been to a hospital, perhaps, you've seen MRI magnets. This is something like 8 Tesla or 10 Tesla magnets. And what we do is we put a radio in this very strong magnetic field. And so this radio could come in many different shapes and sizes, and I'll explain that in a bit. Here, this is what we call a cavity, a microwave cavity. And believe it or not, that is a radio. But in that magnetic field, the photon would be generated, and then you would detect the photon. But I keep referencing radios, and radios might have been more familiar to sort of previous generations, but many younger folks might be more familiar with like the radio in a car, for example. And it used to be that this technology was relatively accessible, and now it's becoming a little more obscure. So I want to go through how radio actually works. There are two critical components that I want to mention. The first is the capacitor. And so this is indicated by the parallel plates on the left-hand side. And the second is what we call the inductor, which is indicated by these loops shown on the right-hand side. And so these are usually indicated by L and C. And then we also have a resistor, which impedes the flow of electrons, indicated by R. And so we typically call this an RLC resonator. That's another term for radio. And the radio stores energy in two forms. It can store energy in the form of an electric field between the parallel magnetic plates in the capacitor. And so the electrons would start to circulate and build up that field in the capacitor. It can also store energy in the form of a magnetic field in the inductor. And so once again, the current would flow and build up a magnetic field in that inductor. And the key here is that it keeps oscillating between the two. And in fact, you can calculate what frequency it is most sensitive to by multiplying the inductance and the capacitance together and taking 1 over the square root of that. We call that the resonant frequency. Okay, and so this is our radio, and it is most sensitive at that specific frequency. Now, we can change what frequency it's sensitive to if we just change these two components. So here, I made this so that the frequency is now higher. And you can do it again and again. Now it's even higher. And so that's how we tune our radio. We just adjust these values as we see fit to be sensitive to the frequency we're interested in. And so this is another way to depict this. We have power here on the y-axis and frequency now on the x-axis. And the resonant frequency is the peak at which you draw the most power, okay? And so as we tune, that peak is going to move, you'll see. And this is like tuning the dial on, well, there used to be a dial in your car for the radio. And the truth is, you know, I gave you the circuit diagram, but it's not as set in stone as you may believe. And so there are many things that actually sort of mimic this behavior that could be grouped under the broader category of radio. In fact, you can even use a coffee can to build a type of radio that is sensitive to Wi-Fi signals. So this is up around 2 gigahertz or so. And so radios are sort of loosely defined. As long as it's an object that has some capacitance and inductance, you can essentially build a radio. And so our experiments therefore come in all shapes and sizes. And the first one that I want to talk to you about is called the Axion dark matter experiment. We also go by ADMX. So this is the ADMX collaboration, and we consist of about 50 people across a variety of institutions located both domestically and internationally. ADMX functions at the University of Washington, where I did my postdoc. You can see here this beautiful picture taken by National Geographic. It was looking for dark matter since about 2018. So dark matter specifically at DFSE sensitivity. So this is that benchmark that we talked about. And when I arrived in about 2019, I was set up to sort of commission the experiment and take data and do an analysis. So it was a very exciting time. But how does it work? We call this a cavity haloscope, and essentially what it is that coffee can, but much bigger, made of copper, sitting in a very strong magnetic field. Again, that's a magnetic field of about 8 Tesla. And we cool the whole thing to be colder than space. So space is about 2.7 Kelvin, and it's actually colder than that. So it's about 0.1 Kelvin. An axion is then expected to interact in the magnetic field and turn into a photon. That causes an electromagnetic signal to ring up this cavity. So this is just like our tunable radios that we saw before, where you have this oscillating current. We then place a wire into the cavity, and it picks up that signal. And the signal then propagates through a series of amplifiers before being processed to generate a power spectrum. So you can see this power spectrum on your right here, where we're plotting the signal to noise ratio as a function of frequency. And you'll note that it's a bit narrow, but there is a peak right around 700 megahertz. And so this is what an axion signal would look like in our data. Essentially, you have a narrow band peak situated at exactly 1 frequency, and that frequency can then be converted to the mass of the axion. But of course, we don't know what the mass of the axion is, right? And so we have to tune this radio. But how do we do it? It looks like a coffee can. Instead of what I mentioned before, we basically put these 2 long, what we call tuning rods. So these are metal cylinders going down the length of the cavity. And what that does is it changes the inductance and the capacitance of this system, right? And so that allows you to tune. And so to give you a more lifelike view of this detector, you can see here a photo from University of Washington around 2019 or so. The cavity is this copper cylinder at the bottom. So it's about person size. And then you have what we call the helium reservoir, which stores liquid helium, and then a variety of components sort of leading up to the top. And what we do, and what we call the rigging operation, is we take this whole apparatus and we drag it over and put it in this magnet bore shown on your right. And so that magnet bore is essentially a hole in the ground. And you can see when it's open, there's actually nitrogen gas kind of bubbling up. And it's very cold. And we put the detector in there, and then we hook everything up and we start taking data. But how do we get such a sensitive radio? We use two factors here. The first is we use what we call a dilution refrigerator. And this dilution refrigerator allows us to reach these sub-millikelvin temperatures. Okay, so again, I said this is colder than space. That is important because we need to reduce the motion of the electrons in the material to achieve sufficiently low noise. And cooling slows down the electrons, right? The other thing that we do is we use what we call quantum amplifiers. And you may be wondering, what are those? And they're a bit unique and new, so this warrants explanation. So quantum amplifiers boost the signal strength while adding very minimal amounts of noise. In fact, sometimes they add the least amount of noise you can possibly add according to physics. And they are made of superconducting circuits, and they require pretty intensive nanofabrication skills to make. So you can see here just some of these examples of quantum amplifiers, and you can see the scale. So this is 2 millimeters, and you can see there's this, we call it a meander of wire just looping back and forth. And that's sort of a testament to how difficult these are to make, because you have to really have the right tools and be good at making these very precise circuits. So then if you use these tools, how sensitive is your radio? Well, it turns out these days you can be pretty sensitive. You can in fact detect 10 to the minus 23 watts using our radio. And this is enough that if you built a phone of equivalent sensitivity on Mars, you would get 4 bars of cell service. So yeah, so for those of you who might have seen The Martian, I think, you know, Matt Damon did a lot of good things, but he should have built like our detector and just called someone for help. I don't know why he didn't do that. So ADMX is taking data, which is very exciting. And so where have we looked so far for the Axion? Well, this is what we call the exclusion limit plot that we set when I was there at the University of Washington. And we'll go back to our 2 parameters that we're curious about, right? We have this GA gamma gamma term, which is the strength of the interaction. And then again, we have the axion mass, in other words, the frequency, okay? And so the colored in regions show the places that we've looked already and haven't found anything, okay? So we've been doing quite a good job chugging along at what we call DFSE sensitivity. So that's like QCD axion. And so far, no luck, but you never know. There might be a detection at any moment. And so it's quite an exciting time to be working in the field of axion physics. The experiment will continue tuning towards higher and higher frequencies, looking for the axion in the coming years. And who knows, we hope that things will be promising. Okay, at this point, I'm going to transition to the other experiment that I work on, which is called the dark matter radio. So dark matter radio is a collaboration of people that is relatively new, and we are a group of people located throughout the United States. You can see here, there's several people on the East Coast and also on the West Coast where the site is. And so here is a photograph of these wonderful people from October 2022, apple picking, and when they went to a collaboration meeting in Massachusetts. And how does DM radio work? It's a bit different from the coffee can experiment I just described. And in fact, we call it a lumped element experiment, or a lumped element haloscope. And the reason we call it that is because it uses discrete components. So if you recall the original diagram of the radio that I showed you, that's an accurate, very accurate representation of DM radio. And so what you have is you have this circuit sitting in a magnetic field, once again. And that signal gets picked up by your tunable resonator, and once again gets read out by quantum amplifiers. And the precise magnet that we use is a bit different from the one on ADMX. So the one on ADMX is like an MRI magnet. It's a big solenoid. The one we use for DM radio is a toroid. And so it looks something like this. So this is showing half of that toroid. And toroids create magnetic fields going around like a donut, like this. Okay, so that's our magnetic field, which is shown here in red. And if an axion comes in and interacts in that magnetic field, it once again creates a photon, which is our signal, right? And so that signal will be sloshing back and forth in that region where the magnetic field is. And it's sloshing because it's AC, remember. So these radios pick up alternating currents. And it turns out in electromagnetism, when you have an alternating current, you also create an alternating magnetic field. Okay, so this is the principle of electromagnetism. And this magnetic field here is shown in blue. Okay, so that is also our signal. It's just being flipped into a magnetic field. And that magnetic field is capable of driving our resonator, driving our radio, okay? So our radio is now, this time it's a giant inductor, okay? Coupled to a capacitor, not shown here, but most of the volume is taken up by this inductor. And that signal can then be read out in a similar fashion using a quantum sensor. And so we use slightly different sensors than ADMX because we're at lower frequencies. In fact, we use something called a squid. So this is showing the readout via the squid amplifier, which then goes to our data acquisition system. And the signal, once again, would look like this power spectrum shown here, where you've got a significant amount of noise shown in blue, and then you've got the singular peak, which would be at the frequency or the mass of the axion. And so the question is, what is the progress that we have made so far on DM radio? And so DM radio is actually a series of experiments. And right now we're working on what we call DM radio 50 liter. So DM radio 50 liter is located at Stanford. And it uses this toroidal magnet. And we build the resonator by winding an inductor. So our collaborators at Princeton are winding the inductor. And then we build a tunable capacitor made of the metal plates. And we hook that up together and test it. So this is showing the resonator testing in a cryostat at Princeton. And this toroidal magnet is fairly unique. Many companies are familiar with building MRI magnets, but people are maybe not as familiar with building toroidal magnets. And so it's quite an engineering feat. So we actually work with a company who is remote. They work out of Boston called Superconducting Systems, Inc. And we actually collaborate with them by designing sort of structural and thermal connections and doing all kinds of simulations. And then they sort of assemble it and test it and are currently in the process of validating it there at their company. And so you can see here, they've actually made pretty good progress. This is showing, the picture in the middle is showing what we call the mandrel. So this is the sort of metal structure that is supporting all of the coils. And you can see the sort of copper color is the winding of the magnet coils. And so this ends up generating, as I stated before, a field going sort of around in a donut shape. And so what is the goal of DM radio? So DM radio is not quite yet taking data, but we have certain sensitivity targets that we hope to achieve. So in the near term, we're going to commission and operate DM radio 50 liter. And so this will cover the region shown in yellow, which is around 10 to the minus 15 inverse GeV for the signal strength. And then it will cover a mass range from 20 PeV up to 20 NeV. So this is nano electron volts. Which corresponds to a photon frequency of 5 kilohertz up to 5 megahertz. Okay, so again, this is just this region here shown in yellow. Beyond that, we really want to upgrade to another experiment called DM radio meter cubed. And DM radio meter cubed here is shown in turquoise, and it goes up to higher frequencies and actually tries to hit that QCD axion band, right? Because that's our benchmark. And fun fact about DM radiometer cube is it's slated to be sited here at SLAC. So we're really looking forward to getting that magnet set up here. And it will hit sensitivity to the DFSC axion between 100 nano EV and 800 nano EV, which corresponds to 30 to 200 megahertz. And then it will achieve sensitivity to this other model, the KSVZ, from 40 NeV to 100 NeV, which corresponds to about 10 to 30 megahertz. Okay, and so that is really going to be the first time we reach for that QCD axion. The last experiment shown here is called DM radio gut, and this is shown in red. And you can see that DM radio gut actually hits that QCD axion band at DFSC all the way down. And that's quite challenging because it gets harder and harder as you go to the lower frequencies to hit that. And so the mass for the DM radio gut experiment will cover about 0.4 nano EV all the way up to 100 nano EV. And again, this corresponds to 100 kilohertz up to 30 megahertz for the frequency of the signal that you're looking for. And so once again, we're all very enthusiastic that operations will be coming soon. And so we're commissioning at Stanford for the 50-liter experiment this fall. And we're hoping to sort of have results close to the end of the year. So what happens then if we find it? What if we find the axion? We haven't actually covered that. We keep talking about excluding regions of parameter space. So a fun fact about dark matter is that it is all throughout the galaxy, right? And as we're moving through the galaxy, we can model it as being more or less, in the same place, but we're moving, right? And so as we move, we're creating effectively a wind that we're passing through. So we call that the dark matter wind. And this is actually observable in the event that we find an axion. And so if we find an axion, what will we do? Well, first we want to study it very intensely and learn as much as we can about the dark matter halo around us. And we do that by just taking a lot of data at one place, at one resonant frequency, right? And so if we zoomed in on that data very, very much, so this is zooming in on that peak that I showed you before, we would see something that looks like this. So it's not, I told a slight lie in the beginning, it's not a single peak. It actually has a little bit of shape to it. And you can look at this paper and they will tell you exactly what that shape is. So it looks like this. And if you sit there long enough taking data, you will actually notice this peak start to shift. And that is due to the dark matter wind, okay? So we can get a sense of the dark matter wind from making a long enough observation at the signal. And you will see what that shift looks like in the animation I'm about to show. So it looks something like this. You can see that peak just shifting ever so slightly to the left here. And so the fun fact about axions is if we ever found them in the lab, we could actually build these little cavity searches in a typical high school level physics experiment, okay? And then you could make observations like this with your little, basically a radio kit, but this time instead of a crystal radio kit, you have an axion radio kit. And I just think that's the most fantastic thing. So I sincerely hope we discover it so we can actually build that kit. And so to wrap things up, I just want to emphasize that this is a very exciting field for a few reasons. And one of the reasons is because we're really operating at the cutting edge of a few fields here. And I've noted two of my favorites. The first is quantum information science. So you may have heard the word quantum thrown around a lot these days. Quantum information science is typically abbreviated QIS, but it relates to things like quantum computing or quantum sensing or quantum amplification, like we just talked about, okay? So this is really developing those tiny circuits and developing the nanofabrication techniques to build these tiny circuits that are so powerful and able to amplify our signal to a level that we can actually detect. So progress on this front is essential to being able to detect the axion. The other field, of course, is particle astrophysics. And so this is where I have my roots in my PhD. And so we're interested in understanding sort of these symmetries of the universe We're interested in understanding physics beyond the so-called standard model, so new physics that we haven't heard about before. And we're interested in cosmology. So axions are at the intersection of all these things. So it's a very exciting field to be a part of. Okay. And actually, that's all that I have today. So in conclusion, I hope I've gotten you excited about axions. Radios can be repurposed to look for dark matter. And new techniques from these fields of quantum information science and quantum measurement are really accelerating the search. And so it's a great time to be working on these experiments, and a detection could happen at any moment. So I want to say thank you, everyone, for coming today, and that's the end of my talk.
Well, thank you very much, Chelsea, for a very interesting talk. We can now take some questions from the audience. And there are two microphone runners on each aisle. So I'll give them microphones. Raise your hand and be recognized. This lecture is being recorded. So please wait until you get the microphone to ask your question. And then with luck, Chelsea will give you the answer. So let's please go ahead. You're first.
Yep. Thank you so much for the talk. I'm curious, like, what limits you from picking a certain band when you're investigating? Like, why couldn't you pick a larger band of area to look for axions?
Yeah, actually, that's a really profound question. So the question, I think, is what limits your bandwidth with these detectors? Is that correct?
Yeah.
Okay, that's actually a really profound question. And actually, that's a focus of my research here at SLAC. Several decades ago, like in the 1950s or so, electrical engineers figured out that receivers have radio receivers have some fundamental constraints into how wide their bandwidth can be, right? So if we go and I don't know if I'm allowed to go back through slides here. I think I can go back. Here we go. So if we go back and we look at this slide, right, there's some maximum bandwidth here. And usually when you try to make it more broadband, the sensitivity goes down. So the trick is, how do you make it broadband without compromising your sensitivity? And it turns out it's really hard to do because in fact, it's a fundamental theorem that passive, linear, and time invariant systems have this limited bandwidth, okay? And so people try to break those three things. They try to make active circuits, for example. What this means is you use circuit components that you deliver power to, like transistors, okay? So people try to sort of get around the rules, I guess, and design more broadband experiments, but it's really hard to do.
Can I just make a comment? There's a trade-off between, you have to scan these 10 orders of magnitude, as Chelsea explained. So there's a trade-off between how fast you can scan and how narrow the bandwidth is, which is to say how strong the signal is. But the axion, the real signal, is extremely narrow. So once you know what the mass of the axion is and find the real signal, you can go to very small bandwidth or very high Q, and then it should be there. And it should be there in every high school classroom in the world.
So about axion detection, right? I think you talked about we think it could be like a spike, but we think like single axion and population of axion would behave the same way. And if it's a population of axion, give you some more observable behavior that may be a little bit easier to detect.
Okay, that's a really good question. So I think it requires a little bit more context than what I initially gave you. So the question is, what is the difference sort of between a single axion versus a population of axion when you're doing this detection? I think that's correct, right? Right, many times during this talk, I mentioned an axion comes in, interacts, and creates a photon. So the reality is it's more like many axions come in and create many photons. And so that is sort of the reality, and the more interactions you have, the stronger your signal is. And so actually this parameter that I call GA gamma gamma, which indicates the likelihood of an interaction happening, sort of the stronger that, well, the more likely your interaction is to happen, the more likely you'll have that conversion, and the stronger your signal will be, right? And so you, but you can do some things to sort of increase your chances of converting the axion into a photon. And one of those things is to increase your magnetic field. So something I didn't talk about is the power of the axion depends really strongly on the magnetic field. It depends on it like the magnetic field squared. And so one of the key features of this field is we're always trying to figure out how do we get bigger magnets. And there's some other people who care about big magnets too, like I talked about MRI folks and everything. And so, but we are definitely motivated on that front. We're also motivated to create what we call really high Q resonators. So these are resonators that sort of don't have a lot of resistance or dissipation. So superconductors are really good for that. So sometimes we think about making resonators out of superconductors. The last thing we do, or there's a few others, but the last major thing that we do is we increase the volume. So the axion signal power depends on the volume of your detector as well. And so you can sort of, you have all these different handles on your experiment that you can sort of toggle to see if you can increase that likelihood of actually detecting a signal. Yeah. Thanks.
Oh, yeah.
Yeah.
You mentioned at the beginning that this work could take you towards the unified theory.
Yeah.
How that works? How it takes you there?
Yeah. So the question is, how do these connect to grand unified theories? And this is actually a very advanced question. And so there are people here in the audience who are much more likely to be able to answer this, including Michael Betzkin and Helen Quinn. And I am an experimentalist. So I think I'm going to defer for now, but it's a very good question, is how do they, what is the precise mechanism? I think the answer kind of depends on, you need many years of study for that one. Yeah. You have a good public lecture answer? Okay, great.
So, so the fact that the axion is very weakly coupled to electromagnetism has to do with the fact that it comes from a high scale in nature. So it corresponds to, that coupling is generated by particles that are very much heavier than the ones we can produce in accelerators. And also the mass is generated by such interactions. So the lower the mass of the axion, the higher proportionally the mass of the particles that give rise to that effect. So when you move this way on the diagram towards smaller masses, you're accessing higher mass scales. And the edge of the thing that she called the gut dark matter radio, that's the grand unification scale. So if the axion is really at that tiny mass, which as you've heard is incredibly challenging to detect, you're actually looking at physics that occurs at the grand unification scale. So that's the dream. See how they can do it.
So when you've got a particle with a wavelength of 100 or even 1,000 meters, how can you capture it with a resonant cavity that's much smaller than that?
Right. So the question is, if you have a particle with wavelength of hundreds of thousands of meters, how do you capture it with a cavity that is much smaller than that? And so that's a good question. I think it requires a little bit of nuance. So the trick here is what do I mean by wavelength? So there is every particle has an associated wavelength, but it's not a description of the physical size of the particle, right? It is a description of how that particle interacts and behaves, but we're not actually saying this thing is that size, right? So there's a little bit of a distinction there. But the fact that these particles have this long wavelength does mean that their behavior is different from normal particles. And it means that they behave more like waves. And so that is actually why we use these radios, which are good at things like waves that are coherent. They're good at detecting that sort of thing, to search for axions rather than, say, a vat of liquid where you have to look for this thing to bounce off of an atomic nuclei. Does that help? Okay, thank you.
Going back to the sort of quilt of your dark matter radio parameter exclusion space, can you talk as an experimentalist about essentially the speed with which we can explore that space, like given the relative fidelity and bandwidth trade-offs you were just describing earlier?
Yes.
It seems like it'd be hard, or that's the one.
The biggest challenge in our field. So this is a very good question. The question is, how do you how fast can you go, essentially? How fast can you scan over this parameter space? And the unfortunate answer right now is not very. And so you can kind of tell this from our plot, actually, because you see that there's these very, very narrow limits going down into the yellow band, into the QCD axion band. And those narrow limits show you just how hard it is to get there, because there's essentially nothing else in that region right now. The scan rate depends on the axion signal power in your cavity. And so this is what I was referring back to when I said the axion signal power scales with the magnetic field squared and the volume and also the quality factor of your cavity. And so if you make those things bigger, you can go faster. But that's a big challenge, and magnets are expensive. And so it's really quite challenging. And usually we're going on the order of several hundred megahertz per year with the ADMX experiment. And so if you look at this parameter space, I mean, this is this region here shown in red, that's not much, right? And this parameter space is just a subset of, it might actually expand beyond that. So it's a really daunting task. And this is where like a huge chunk of our brain power is going right now, is how do we solve this problem? Because there's been a lot of progress made in these sort of more traditional dark matter searches, but axions are still, to some extent, the technology is a little bit newer. And so we still really have to solve these problems. And yeah, the world of quantum sensing is a huge boon in that regard, because that's really what's helping us even get to the sensitivity in the first place. So yeah, definitely challenging.
Thank you. Is there any reason to believe that the dark matter is only consisted of axions, or is it possible that it's just a mixture of a lot of different things?
Yeah, good question. I think the question is basically, is the dark matter, would it only be axions, or could it be a mix of things? It could definitely be a mix of things. We don't really know. The axion is compelling because it can make up all of the dark matter, which not everything can. But you could, in principle, have situations where you have several axions, or axion-like particles, we like to call them, sort of located at a variety of interaction strengths shown here. So if we find something, there's actually no reason to stop looking. We might want to keep looking and see if there's anything else out there. But we don't know. So yeah.
I know you said that dark matter can act as a wave or a particle. Are your experiments ever sensitive to eyesight?
That's an interesting question. Yeah. So the answer to that, again, just repeating so everyone can hear, our experiments sensitive to eyesight because our eyes are also sensitive to waves, right? They're sensitive to electromagnetic signals coming in, and electromagnetic signals are always waves. And so the answer to that question is the optical band is way up here, and so it's that way, and so we're not really looking up there. I mean, that requires different types of technology. And so for the experiments that I've described today, we're at lower frequencies, and so it's not visible to the eye. But even if it were visible to the eye, it would be extremely low single photons, pretty much, that we'd be counting. So yeah.
You mentioned photons are the signals to detect axions. Could you go into more depth of the mechanism for converting an axion into a photon when the wavelengths are so different?
Yeah, so the question is, how does what is the mechanism for the axion converting to the photon when the wavelengths are so different? So I think there might be a little confusion here. So the wavelength of the axion is very, very large. And actually the photon it converts to also has a very large wavelength. So energy is conserved. And the math works out, I guess is what I'll say. In terms of the mechanism, this is sort of predicted by, so the axion would basically alter Maxwell's equations. So this is a little bit advanced, but in electromagnetism, you have these equations that describe electromagnetism called Maxwell's equations. And so they would actually modify those in such a way that you would be able to create this photon. If there are theoretical aspects to add here, I don't really, I think that's the extent of what we know. Maybe.
Just that the axion detector is huge. The wavelength is huge. So the detector breaks momentum conservation. So when the axion converts to a photon, energy is conserved, but once it occurs, the momentum is not necessarily conserved. And so the wavelength can change. And so what happens is that the oscillating signal from the axion wave turns into the oscillating signal from the photon, and the wavelengths don't have to.
So speaking from a fellow ham,
Nice.
that
one in the audience. I was
there's
like,
got to be one.
Yes.
There's got to be one. One of the detectors you were looking at is in the 2-meter band, and I start thinking, do you ever have any issues with getting crosstalk from signals here? And would it make sense to put it far away from the Earth in order to lower the noise?
Yeah, that's a great question. So the question is, do we ever have crosstalk from sort of ambient radio noise here on Earth, basically, caused by amateur radio operators or caused by, AM radio stations or whatever you call it? And the answer is we absolutely do. So the funny thing is we do shield. We have some electromagnetic shielding, but actually you don't need to do that much. You can shield it, but there are other ways to rule out signals that could be from sources that are not the axion, right? So the axion would only interact in the region where there is a magnetic field. And so what this means is you could look at how the axion gets enhanced on resonance and then diminishes off to verify that in fact came from that cavity that we talked about. So that's one clue. The other clue is you shouldn't be able to detect the axion just ambiently in the lab. So if I go in with my ham radio and I wave an antenna in the air, I shouldn't be able to detect it because that radio is not sensitive enough, right? So if I am detecting a signal at that exact frequency in the lab and then also in the cold cryogenic environment of the experiment, that's a sign that probably isn't the axion, and we should try to shield out that signal or find another way to eliminate it. And so we actually do this, it's kind of like an active veto system where we check. But a funny story is you do actually have signals that appear from radio stations, for example, and you can go look up what frequencies, what bands they're coming from and so on. And in fact, one time we did have a radio that was nearby at the University of Washington. And what you could actually do, which is kind of hilarious, is you could take the signal and you could demodulate it and you could put headphones in and you could listen to it through our detector. And so it is like the most advanced radio you've ever seen. And in fact, if we found the axion, we could do the same thing. So you could listen to the axion. So I really hope that's part of this crystal axion radio kit that we can build one day. Yeah.
Hello? Okay. I know that the axion is more like a wave. Is there a way to force it to be more particle-like?
I'm sorry, I didn't catch that.
Sorry, I mean, we said that the axion is more wave-like than it is
Yes.
particle-like. Is there a way to force it to be more particle-like?
Yeah, so the question is there a way to force the axion to be more particle-like? I'm thinking. Yeah, I'm not sure. I mean, its fundamental nature is wave-like. I'm not sure if there's a trick you could play unless you're converting it to something else. Yeah, it's an interesting idea. I don't think I have an answer right now, but yeah. Oh no, you're good.
So a very high energy axion would behave like a particle. And if you went to the LHC and got some really high energy particles and they emitted axions, then you would actually see them as electromagnetic bursts. Of course, with these very low couplings of the axion to electromagnetism, you'd have to wait about 1 million years to see such an event. But such an event would have the axions. But better to wait for these guys to discover it first. Okay, Chelsea, thank you very much. It's been a great talk. If you'd like to discuss more with Chelsea and her colleagues, we'll be out in the lobby in just a few minutes. We just have to clear up and get out of the auditorium. And at the beginning of October, there will be the next one of these on a very different subject, having to do with environmental chemistry. So, but we do lots of things at SLAC. We encourage you to come back for that and tell all your friends. So until then, thank you very much for coming. We really do appreciate it. And we look forward to the next one.